And I think it's about 2 minutes after the hour, so it's about time to get started here. I want to thank everybody for joining in for the first MIDAS webinar of 2024. My name is Harry Hawkeiser. I'm the director of the MIDAS Coordination Center, and I'll be your host for this meeting. Today, we're very pleased to have Liam Critcher as our speaker. Liam is a third-year PhD student in applied probability at the University of Nottingham, where he's also got a master's in statistics from Nottingham, and his current work is focusing on epidemics in structured populations such as households. So I think before I hand it over to Liam, I just want to thank him for joining in and to reiterate that we'd love to have more students presenting work in progress. We have a pretty full schedule booked up all the way through June of this year, but if you're interested in presenting for the webinar, please let us know and we'll see if we can get you on the schedule after that. So with that, I want to thank Liam for joining us to speak, and I'm going to hand the floor over. So Liam, please take it away. We're looking forward to hearing your talk.
Thank you very much. Thank you to MIDAS for inviting me as well to talk. It's much appreciated. And thank you to everyone who's attending, whatever time it is. I know UK, slightly less friendly time, but yeah, hopefully it's worth the wait. So the talk is about the impact of household structure on disease-induced herd immunity. So it's joint work with me and my three supervisors, Frank Ball, Pete Neal, and David Sell. So here's just a brief outline of the sort of structure of the talk. So I'm going to start by outlining the homogeneously mixing epidemic, which is quite a simple but important epidemic model, which is kind of a good basis to start with these problems. I'll then briefly go into the sort of idea of herd immunity. Then the model that I'm actually interested in, which is the households model, which kind of self-explanatory, but I'll go through some of the sort of details and properties. I'll then kind of combine these two, so talk about herd immunity within the households model, some results, both analytical results where we can actually prove things, and also some results where we suspect something may be true and we have maybe numerical evidence that it's true, but we don't have a proof, but we have, you know, strong numerics to back up our arguments. And then I'll lightly touch on some potential avenues for future work. And so my sort of plan for the talk was that if there's questions that are sort of just curiosity questions, then I'm happy to answer those at the end. But if there's a question where something seems completely wrong or completely, you know, not understood, then feel free to let me know. If it's kind of an urgent question, then I'm happy to treat that one as and when. So all of the results that I'm going to present today are sort of tip of the iceberg of this paper. Hopefully, these slides will be available after the talk. So if you are interested and you want to have a look at kind of the more minute details, then you can do that. And obviously, feel free to ask me questions either before or after reading that. Okay, so as promised, the homogeneously mixing epidemic. So we're using a standard susceptible, infective, removed model. So those are the three components, S, I, and R. If we have an infective and they contact a given susceptible, then they make that susceptible become an infective. So they transition from the susceptible state to the infectious state. We're assuming that two things. One, that there's a small number of initial infectives, and two, that the population is a large population, which is closed. So by closed, I mean there are not people joining and leaving. There's no demography in the model. And yeah, there's a small number of people who initially start off infectious, and they will then begin infecting others. These global infections, as we call them, occur from a given individual to a given susceptible at rate which we call lambda G, scaled by the population size N. And this is person to person. So if we think about one infective, the rate at which they contact the entire population, well, there are N members of the population, and there's an N in the denominator of this fraction, so those will clear one another, and the global contact rate would just be lambda G. The infectious periods are independent and identically distributed for each individual, and they follow a random variable, which we call TI, which typically has an arbitrary but specified distribution. And in some places, we'll assume that the moment generating function of that distribution is finite, but I'll go into more about that a little bit later. So here's a little diagram which kind of summarizes what I've just been saying. So we've got susceptibles, infectives, and removed. And essentially, the transitions, if they happen this way along the diagram. Once you're removed, you're assumed to not be reinfected, so you essentially play no further role in the epidemic. You're just counted out, as it were. Okay, so there's an important quantity in these homogeneously mixing epidemics, which is known as R0, which you may or may not have heard of over the last couple of years. And it's known as the basic reproduction number, which we find by using a branching process, which basically approximates the number of infected individuals. So the idea is that in the early stages of an epidemic, the epidemic looks like a branching process because it's very unlikely that a given individual will get contacted twice, because there's a large population and there's a small number of infectives. So there's already a low probability of being contacted. So the probability that you get contacted more than once, we can treat that as being very small. So this allows us to do a coupling between branching processes and the epidemic process. And owing to this branching process behavior, the epidemic can take off, which means that a non-negligible fraction of the population become infected with strictly positive probability if and only if this reproduction number R0 is larger than 1. So kind of the key idea here is that, roughly speaking, branching processes will grow like the offspring parameter, which is R0 in this case, to the power of n, where n is the number of generations. So if the offspring parameter is larger than 1, you're taking a number larger than 1 to a high power. That's going to get very big. Whereas the mean of the process is going to get smaller with n if R0 is less than 1. So R0 is the average number of new infections which is caused by a typical infective in the early stages of these epidemics. So here's the expression for R0, which I'll now sort of briefly explain. So we've already said or discussed the fact that a given individual, if they're infectious, will contact globally overall at rate lambda G. So that's their kind of average contact rate. And all this is saying is that the average number of new infections is the average contact rate multiplied by the mean duration of the time of which they're infectious. So they're infectious for, on average, E of Ti time, and during all that time, they're mixing at rate lambda G. So that's kind of where this formula comes from. So this slide basically is just a small illustration of the idea that R0 is a threshold parameter. So epidemic, as I said, could take off, has the opportunity to take off if and only if R0 is larger than 1. So R0 is a threshold parameter, i.e. it is informing us, can an epidemic take off or can it not? And if we look at this diagram here, as we increase R0, we can see when it's less than 1 in the first plot in the top left, there's only one type of epidemic happening where there's a small final size. By final size, we just mean the number of people infected. So there's a small number of people infected in the epidemic when R0 is 3/4. Again, when R0 is 1, again, R naught is not greater than 1 here, so we're not having this second density. But then when we take R naught bigger than 1, we're getting this second density away from 0, and this is corresponding to what we refer to as a major outbreak, or a large outbreak, or the epidemic taking off, which is where there's a strictly sort of larger than 0, or a non-negligible fraction of the population that are being infected, I should say. And it's also clear that if I increase R naught higher above 1, it becomes easier to distinguish these minor and major outbreaks. So when R naught's 1.25, there's kind of a little bit of density crossover between the minor and the major, but we expect this to go away if we increased R naught further above 1. And indeed it does. You can see in the fourth plot there in the bottom right, that is the case. So we're going to assume that vaccinations grant individuals immunity to any future infection. So essentially what a vaccination does, if we think back to the SIR diagram, is it puts individuals in that removed bracket because they can't be infected, they can't contribute to infection, they are just, it's sort of eliminated from any further analysis. So in this homogeneous model for now, if we suppose that we vaccinate a proportion V of the population, well, the population will become less susceptible to infection because some members, if contacted, nothing will happen because they're immune. So if I now define a new R naught, which I call RV, the post-vaccination threshold parameter, which is basically, okay, what's the threshold parameter for an epidemic where I vaccinate a proportion V prior to the epidemic? Well, in this case, we just have RV is 1 minus V times R naught. Well, why is that true? Well, if you think back to what RV actually is, it's saying what's the mean number of contacts from a typical individual? Well, if that individual is vaccinated, which is true with probability V, they'll have no contacts because they won't be infectious. And if that individual is not vaccinated, which happens with probability 1 minus V, then the same logic from before applies, and they'll have R naught mean contacts. So in the end, we have a reduction in the threshold parameter by this factor 1 minus V. It seems quite reasonable because if V was 0, i.e. if we didn't vaccinate anybody, we would just have the basic R naught again. And if V was 1, then we would certainly expect no mean contacts because everybody's safe in that case. But the kind of crucial point I want to make here is that from the previous slides, we'd seen if RV is less than 1 or less than or equal to 1, we say that the epidemic is subcritical, which means it can't take off. And in this calculation, if we take our vaccination coverage, as we call it V here, to be larger than or equal to 1 minus 1 over R naught, then RV will be less than or equal to 1 and will have prevented a major outbreak. That's kind of the key idea of herd immunity, but applied in a slightly simpler case than the one I'm going to consider in this talk. And if, as I said here, if R naught is less than or equal to 1, then we say that herd immunity has been achieved. And it's sort of called herd immunity because the idea is the population are now protected, because if an epidemic starts, it's not going to take off. Okay. So, as I mentioned, a population with a threshold parameter which is less than 1, we say that's achieved herd immunity, there won't be a major outbreak. But for more complex models, this vaccination and disease spread can require different proportions to be infected. And what I mean by that is, if you vaccinate uniformly at random, that may not actually achieve immunity as quickly or as slowly as allowing a first epidemic to spread and saying, okay, what happens among a new epidemic among the remaining susceptibles? So for example, in the model with age and activity level, there's a reduction from about 60% with random vaccine allocation down to around 43% when age and activity level are included. And this was for an R0 2.5. But kind of the key idea here is that when the epidemic runs in a population with heterogeneity, more active individuals are more likely to be infected first, and that will more quickly reduce the susceptibility of the population. And in this sense, we say that the disease spread can sort of act like a targeted vaccine, as it were. So this was studied in Britain et al., which was the paper to do with age and activity structure, which found quite a dramatic reduction in the herd immunity level compared to random vaccination. But similar work was done with variable individual susceptibility in this Gomez paper. And both of these are, if you're interested in this topic, both of these are worth looking at, particularly the Britain paper, as it kind of informs the strategy that's done with my work. Okay, so the key message here is, if we impose heterogeneity on the population, disease-induced herd immunity and random vaccination achieve herd immunity more slowly or more quickly than one another. And the kind of question is, what happens if we, instead of having individuals stratified by age or activity level, what if we group individuals with a household structure? What happens to herd immunity? Is it larger? Is it smaller? Does it not make a difference? That's kind of what we're interested in. And that's what we're going to find out. So to do that, I'm going to need to introduce the model, which is essentially a household extension of the SIR model. So all of the things I've said about susceptible, infective, removed, all still stand, but we now have this extra layer of structure. So we follow this Ball et al. We have MN households of size N. The households range in size, so we have some finite maximum population or finite maximum household size, which we call N max. And we still have the same total population size, which is N, big N. So global infection occurs exactly as it did in the standard SIR epidemic, but there's now this extra within-house local infection, which happens at rate lambda L. So not only is there extra infection because it's local infection, but it's happening in some sense quicker because it's not scaled by the population size. That's kind of a key point. So the local infection is happening quite a bit faster, which if you sort of think about real life, that kind of makes sense, right? The probability that if I become infectious, the probability that I contact somebody globally, i.e. just somebody I meet on the street, is quite low. The probability that I contact a housemate, we would expect that kind of naturally to be higher. So this is kind of the key point. The infectives, they can contact anybody globally, but only the household members they can contact locally. So I've got two households here. If I consider one infective individual in household 1, they're going to contact each member of household 2 only at this rate lambda G divided by N. But then members within their own household, they'll contact both with rate lambda G over N, because you can still contact a local household member globally, but there's this extra rate, this lambda L, coming from the within-house infection. And I'll mainly be focusing here on when population size is going to infinity. So N going to infinity, because it allows us to use essentially a deterministic model. But I won't go into too much detail about that here. But yeah, this is sort of the key idea. So as I say, we'll assume that the total number of households, which we'll call M, which is just the sum of the NNs, is large. That will mean that the population size itself is also going to be large. So if there are NN households which have size N, then this alpha I here, which is the proportion of the size I households, is essentially the probability that a randomly chosen household is of size I. So I pick a household at random, uniformly at random. I say, okay, what is the probability that that household is size 3? It's alpha 3. And these form a distribution, the household distribution, which we call the household distribution H. But if we look at instead the number of size I households multiplied by their size and divided by the total population, we get the proportion of individuals in households of size I. So this is like asking, okay, if I pick an individual uniformly at random in the population, what's the probability that that individual is in a size I household? And that is alpha I tilde. And these form what we call the size bias household distribution, which we call H tilde. And kind of the key point here is that if I have 500 households of size 1 and 500 households of size 5, almost everybody is in a size 5 household. So this kind of sorts the biasing of the sizes of the household, because actually if I pick somebody at random in that example, they're probably going to be in a size 5, not a size 1. So while alpha I will just be a half at 1 and a half at 5, alpha I tilde will account for the different sizes. Okay. And these alpha I tildes will be useful, very useful momentarily. So in the homogeneously mixing epidemic, we had a branching process at the individual level, which told us whether an epidemic could take off. And what we would like in the household model, in order to be able to look at herd immunity, we need a threshold parameter all the same. But we can't look at an individual level, because earlier I said, well, the probability that an individual gets contacted twice in the early stages will be low, because there's a low chance they'll be contacted. Therefore, the chance of them being contacted again is incredibly low. This is not true in the household model, because if they've been contacted by a housemate, a local contact, that's not necessarily going to happen with low probability more than once. So the coupling between the branching process at an individual level and the epidemic breaks down. But instead, so we have, instead of that individual-based result, we have that the probability that a household is contacted globally twice in the early stages is small. And what this essentially suggests we should do is, instead of looking at an individual level, we should form a branching process at the household level. So again, we use a branching process, but this time each individual in our branching process is an infected household, i.e. a household which has been contacted globally by an infective. We then look at the mean of this branching process, which we call R star, and that has the exact same kind of threshold behavior as R naught did in the homogeneously mixing epidemic. And it means we can do our herd immunity work on R star and work out essentially what proportions of people we need to vaccinate in order to stop a major outbreak. So in a completely analogous way to R naught, the epidemic takes off, i.e. we get a non-negligible fraction of the population infected with positive probability if and only if this threshold parameter is larger than 1. So I'm now going to briefly explain how we derive this. So if we consider an epidemic just within a household, where the within rate is lambda L, there's no external global infection, there's just one initial infective in a household of size N, and we calculate the mean size of that outbreak, so the mean number of people infected, including the initial infective, and we denote that by mu N of lambda L. Then in the early stages, such a household of size N is going to contribute mu N lambda L times by this factor, which is essentially the old R naught, global infections. And the reason that is because we're going to get, from each individual, we'll get lambda G E of TI, but we've got this extra factor coming from the fact that the household has got, on average, mu N individuals who've been infected. as we've just discussed with the size biasing, a typical individual will be in a size I household with probability exactly alpha I tilde. So if I condition on the household size of an individual, that I find that the mean number of infectious households, which we generate by a typical infected household, satisfies this formula here. So as I said before, this lambda GE of TI is just the old mean number infected by an individual. This is the mean number who've been infected in the within-house epidemic, but then we have to condition on what the typical size of a randomly chosen individual is. And if we put that together, we find this formula for R star. Okay. So here's some more simulations, and this is very similar to the work earlier on with R naught in terms of showing as a threshold parameter. So again, the idea, the sort of key idea is if R star is below 1 or less than or equal to 1, our community will be protected. There won't be a major outbreak, and we're kind of in a good spot. So this example here is just with 900 households of size 5, varying R star, and the exact same comments apply really, that the density, the second density only appears if we allow R star to be larger than 1. And so kind of, again, the key point is, let's get R star below 1 somehow, and we'll be in a good place. The community will be in a good place. Okay, I'm going to briefly introduce this quantity PL, which will be kind of used within the talk and plots and whatnot. It's essentially a way of just simplifying presentation of some plots. So if we consider the same epidemic that we considered with mu n of lambda L, so it's within a single household, no external infection, and within household infection rate lambda L, if we denote by 5 theta the moment generating function of the infectious period, which we'll assume exists, then the local infection probability, which is the probability that a given infective within the household infects a given susceptible, is given by this formula here, 1 minus phi of lambda L. And the key point is that if lambda L is 0, there's no local infection, so this probability will be 0. And as lambda L tends to infinity, this will be 1. So essentially what PL does is it maps 0 infinity for lambda L into 0, 1, which means when I do plots and things, I don't have this wasted space towards the end where it's just lambda L is like 10,000. It's all just giving us the same information. It kind of makes it a bit more concise. So that's where it comes from. But the key thing to note is when PL is 0, there's no local infection. And when PL is 1, everyone in the household gets infected immediately, basically. Okay, so now we'll move to sort of herd immunity in the households model. So we're assuming that the vaccination or recovery from infection grant an individual immunity thereafter. They're essentially removed. So just as with R naught, where we had RV was 1 minus V times R naught, the threshold parameter, the threshold behavior rather of R star replies that if we reduce the proportion of susceptibles, then we can prevent a major outbreak. So we'll compare the two strategies of random vaccination, which is where you just give out a vaccine uniformly at random, and disease-induced herd immunity, which is where we run an epidemic and we say, okay, what state is the population in, either at some point during or at the end of this first epidemic, and what would happen if we started a new one with a small number of initial infectives, having had this first epidemic spread and infect some people. So I'll clarify that a bit more in the coming slides. But essentially, here's the idea. We've got a population which is super critical because R star is larger than 1. It's at risk of a major outbreak. But if we reduce susceptibility in the population, we end up in this case where we're subcritical, herd immunity is achieved, there can't be a major outbreak, the population's safe. Okay. So beginning with random vaccination, if we were to assign with probability C uniformly at random a vaccination to each individual, then C would be known as the vaccination coverage. And we could essentially, following ball and line, we could have, in the same way that we had our V earlier on, R sub V, which was R naught as a function of the vaccination coverage, we could denote by R U of C, R star among the remaining susceptibles, once we've implemented this random vaccination. So we're saying, okay, we're going to randomly vaccinate with probability C each individual, and then we're going to look at what happens if we start an epidemic among this population, where some members with probability C just won't take part, and therefore there'll be less susceptibility in the population. And obviously, if we set our U of C to be 1, we can find the classical herd immunity level, which is essentially what's the minimum number that we need to vaccinate. Because obviously, if C was 1, we just said, okay, we're going to vaccinate everybody, then yes, we're going to get a threshold parameter of 0, which is less than 1. The epidemic won't take off. But the fact that our U of C is decreasing as a function of C, which is very natural, as you infect more people, as you vaccinate more people, you're going to have a lower susceptibility. There's this crossing point where we have the minimum number that we would need to vaccinate, and we call that the classical herd immunity level, which is denoted by HC. So don't be scared by this formula. It's fine. So the first part of this alpha n tilde, this is just, okay, we're picking an individual at random in our branching process, where some individuals are now vaccinated. But the vaccination doesn't change anything to do with the household structure in itself. So the probability that an individual is in a size n household is still alpha n tilde. So that's where that first sum comes from. Because we're vaccinating uniformly at random, a size n household is going to have a binomial number of vaccinated members with parameters n for the number of members in the household and c for the probability that they're vaccinated. So this second part here, this n choose v, c to the v, 1 minus c to the n minus v, this is just the binomial PMF evaluated at v. Then if we're in a household which has got n members, v of which are vaccinated, the proportion of those who are still infectious, if I pick one of those at random, the proportion that are infectious is 1 minus v divided by n, because there will be essentially n minus v who won't be vaccinated, and there are n of them in total, so that's n minus v divided by n, cancel down, you get 1 minus v over n. And then among those n minus v members, if this person is contacted, they'll have a within epidemic in the same way as before with parameter lambda L. So this will be the mean number of contacts locally. And then this lambda GE of TI at the end is just the mean number that an individual will create. So that kind of is where this is coming from. It's condition on household. What state is the household in, i.e. how many of them have been vaccinated, and then given V of them have been vaccinated, this is the resulting within household epidemic. And then after we know the within household epidemic, this is the mean number of contacts globally. So yeah, I say it looks a little bit scary formula, but it's kind of, you'll see in a minute, it's kind of a specific example of a more general formula which you find for these threshold parameters after vaccination. Okay, so let's say we can call, for example, our post, we could call it R star among the remaining susceptibles, our post-vaccination threshold parameter. And this will depend on how we distribute immunity in the households. So as I said a moment ago, if we do it randomly on an individual level, then we'll have a binomial distribution within the household. But we could sort of write this more generally and say, okay, if XNV is the proportion of our size N households which have got V members immune to infection, then we could write this as our post-vaccination threshold parameter. And it's exactly the same idea in terms of where the alpha N tilde and the other terms arise from. The only difference is in the previous slide, this XNV was a binomial PMF. But if we chose a different way to spread immunity, these XNV might be different. So this XNV essentially is encapsulating what state the households are in. So are they all either fully susceptible or fully infected? Are they equally likely to be in different states? That's what this is kind of encapsulating. And this will change based on what vaccination strategy you use. So as I sort of noted, XNV is the key kind of encapsulating of how immunity is achieved. And we view this in this work either as a function of time or as a function of kind of a global restriction measure. I'll go into more detail about these in a moment, but we call these RV and RDI. But all of these kind of RU, RV, and RDI are just essentially an R star that has been reduced somehow. So I'll go into more detail about that in a moment. So this is one of the sort of key ideas, which is disease-induced herd immunity. So we start off by just running an epidemic in the households model, and that will infect members as the epidemic goes on over time. And what we say is, okay, what would happen if at time t we just stopped the epidemic and said, right, okay, everyone who's been infected and has been removed, you're all now immune from infection. And what would happen if we started a new epidemic with a small number of initial infectives among the remaining susceptible population? Now, if T was very small, we wouldn't really have had much of a first epidemic. And if T was very big, the first epidemic would have spread quite a lot. So it's hopefully clear that this second epidemic is a function of this stopping time T. So we call this threshold parameter for the second epidemic RV of T. But at some point, there'll be a stopping time where RV of T actually reaches 1, i.e. we stop here and we say, right, if we were to start again a new epidemic from here, we would be subcritical, we wouldn't have a major outbreak. And what we define by HD is essentially the proportion of non-susceptibles. It's the proportion that have been, if you like, vaccinated because they've been infected in a first epidemic. And so their populations achieved disease-induced herd immunity. So there's a little diagram that accompanies this because it's a little bit of a tricky idea to get used to initially. So we're sort of going from the left, we're going right and down on the first diagram. So we want RV of T to be 1. So we wait for RV to cross 1, and it does so at time T star. And then we look at the proportion of non-susceptibles against time, which is going to increase because people are getting infected. And we then take, okay, at T star, we go across and say, what's the proportion of non-susceptibles? And it's our disease-induced herd immunity level HD. So to actually calculate this, it does require deterministic limiting equations for the household model, which I haven't gone into here, but they are available in the paper. They're a little bit scary to look at when you first see them, but they're very sort of natural extension of the SIR model. But kind of the key point is that, you know, we're dealing with this crossing time, and then we're looking at the proportion of non-susceptibles at this crossing time. Okay, so that's all well and good. The problem is that when we have a Markovian infectious period rather, so for example, if we had an exponential or a Erlang distributed infectious period, we can write down these deterministic limiting equations that I was just describing. We can actually, okay, we can't solve them analytically, but we could, you know, we code them up, numerically integrate. We've got a crossing condition, which is RV equals 1. And we can say, okay, what's S when RV is equal to 1? And we can work everything out. But for a more general infectious period, this is not the case. This is owing to the lack of memory property of the exponential, makes things a lot easier to deal with. If we have a more general infectious period, we can't find HD nearly as easily. And it's quite tempting to think, well, what if, for example, we took the infectious period just to be constant? So, oh, it's okay, let's say it's 1 with probability 1. You'd think, oh, it must be easy. It's not. It's still difficult to do anything. You end up with delay differential equations, for instance, and it's certainly not obvious how to proceed if you don't have a Markovian infectious period. So this motivates, we'd like to do some studying of HD still, so this motivates an approximation where we use final size results. Now, final size results essentially means what's happened at the end of an epidemic, and there's a lot more theory and results about epidemics that have been run to termination than there are about epidemics that have been run until time t. So we have this approximation, which is sort of inspired by Britton et al., and we denote this by HD tilde. It's much easier to study, and therefore much easier to compare to HC because it depends on these final size results. So essentially, we're going to introduce HD tilde and then work with it, because in many cases, it's a very good approximation to HD without being nearly as tricky to calculate. Okay, so here's the idea. This is probably the trickiest slide, so it may take a little while on it, but I think it's key to really kind of get to grips with what's going on here. So we now consider running an epidemic where the local infection is the same as previous, but the global infection is reduced by some factor alpha, which will be between 0 and 1. So obviously, if alpha is 1, we haven't done anything. We're just running the epidemic as it was before. But if alpha is 0, then there's no global infection. Obviously, we're not going to get a major outbreak in that case. So we're picking this. We've got this alpha. It's between 0 and 1, and we just run the epidemic, but we run it to conclusion this time. We're not stopping it partway through. We're just running it until it ends, whenever that is. And we then say, okay, everybody in that first epidemic who became infected, they're immune now. What happens if we start a new epidemic among the remaining susceptibles with a small number of initial infectives? Can that epidemic take off? And hopefully it's not too much of a stretch to think, well, that's going to be a function. The threshold parameter for that second epidemic will be a function of the factor that we reduce the global infection rate by, which we call alpha here. So if alpha is very small, we would think that the threshold parameter for the second epidemic would be lower because we've tuned how much infection there can be in this first epidemic. We then choose alpha, we call it alpha star, such that this disease-induced reproduction number is equal to 1. So the second epidemic can't take off. And we say, well, let's look at the proportion who were infected in that first epidemic with this global control measure, alpha star. That's our disease-induced, or our approximation, the disease-induced herd immunity level. So it does things in a slightly different way because it looks at this restrictive factor on the first epidemic, but we're essentially tuning that first epidemic so that the second one is critical. But the key thing is here, because we're using final size results, it's much, much easier to know what's happening at the end of the epidemic. So we can essentially calculate what alpha is, and we can calculate HD tilde. And HD tilde is available, typically only depends, results with it typically only depend on the moments of the infectious period. So we don't have to worry about not being able to solve delay differential equations and all this. This is a much more convenient quantity to work with. So here's my diagram. So I've got a first epidemic with global measures. Second epidemic is critical. And I want to infer Hg tilde. So as a sort of summary, we've got the post-vaccination threshold parameter. We want to reduce it to 1, and it's a function of either coverage, which gives us HC, time, which gives us HD, or restriction measures, which gives us Hg tilde. These depend on what strategy we choose, and we want to compare HD and HC, but we'll do this by comparing Hg tilde and HC, because Hg tilde is a bit easier to work with. As we gather the immunity, essentially the household structure in a way changes because there are fewer members in the household that can become susceptible. So here's a small sort of numerical justification that Hg tilde is quite a good approximation of HD. So essentially, as I said earlier, we can compute this for a much wider range of distributions. And we've got a heat map here with the percentage error. And kind of the key points is that when PL is close to 0 or 1, this error is very small. So it seems sensible to work with Hg tilde if it's a lot more tractable than to work with HD. So when there's no local infection, there are no local epidemics, and this approximation is exact. And similarly, when the local epidemics immediately infect everybody, when lambda L goes to infinity, the approximation is also exact. So we're now going to look at some results in the highly locally infectious case with the common household size. So in this case, we can actually compute these explicitly. So in this case, we wish to, I'll sort of skim the detail of this because it's quite a heavy formula, but we wish to solve this equation. But because lambda L goes to infinity, the mean household size just becomes however many people were in the household. We therefore end up with this expression. And if we invert this, we reach this formula for HC. And now we'll calculate Hg tilde, which is a little bit more complicated. But if we denote by pi the probability that an individual escapes global infection in the first epidemic, so that they're still susceptible in the second, then a household will remain fully susceptible with probability pi to the power n, but will otherwise become fully infected because it's highly locally infectious. So this gives us essentially R star multiplied by pi to the power n is equal to 1 because we want the second epidemic at criticality. So then Hg tilde, the proportion of the people who become infected, well, that's 1 minus the proportion who avoid. That's 1 minus pi to the n. And if we combine these two together, we get Hg tilde is 1 minus 1 over n lambda g e of ti. So if we compare these, we can essentially subtract one from the other, and we find that this is always positive, i.e. the disease-induced herd immunity level is higher than the classical. And in this case, disease-induced herd immunity is actually equivalent to the worst possible vaccination strategy for a given coverage. And that's because it's all or nothing. It's either vaccinating a full household or it's vaccinating nobody, which means it's leaving full households susceptible, which if they become infected in the second epidemic, will become fully infected owing to the highly locally infectious nature of the epidemic. And this difference is maximized when R naught in the household model is 2. I'll sort of, if anyone's interested in that, I can answer a question about that, but it's not sort of key. So recalling what I said earlier about the size bias distribution, if we assume the mean of the infectious period is 1 and the variance is finite, we've got this result, which essentially says that as lambda L is small, we have the difference between HD and tilde and HC depends on the difference between the mean and the variance of the size-biased household distribution. But when all households are the same size, this variance term will be 0. So we have Hg tilde larger than Hc in the common household size case. So we've got an explicit result in the case where lambda L is close to 0 or close to infinity, but the comparison is more difficult in between. But we can show that if n is 2 or n is 3, we always have Hg tilde bigger than Hc. And we conjecture that this holds for a common household size n greater than 1. And kind of the key point here is that the household structure increases the disease-induced herd immunity level. So whereas previous literature found a decrease, household structure increased. This is essentially a plot which demonstrates that. I'll skip this slide because I don't think it's as important as some of the numerical examples. So I've given an example here where we actually infer household distributions from UN data, and we just compare Hg tilde and Hc and Hd, and we choose the global infection rate to fix the early exponential growth rate, which is often what we actually observe in practice. So as we can see in almost all these cases, Hg tilde is larger than Hc. And kind of the key point is, this is contradicting or going against what we see normally, where individual heterogeneity is decreasing the disease-induced herd immunity level. When we add a household structure, it goes the other way. Okay, so possible extensions, having a latent period, which won't change final size results, but would change HD. So it would change HD, it would change HD, but not Hg tilde. A threshold analysis for epidemics which have R star quite close to 1, just above 1. We've got analytical results for households of size 1 or n greater than 1. And essentially, in a lot of these results, it comes down to a condition on the average size and variability, as we saw with the lambda L close to 0 result. But as I say, these results, I hope you believe me, these results are kind of just really scraping the iceberg of the analysis that's available. And if you are interested in kind of the more nitty-gritty details, then I would encourage you to read this paper. So here's a very brief summary. So we've got a threshold parameter R star, which tells us whether an epidemic can take off. We want to reduce it to 1, so we can't have a major outbreak. We achieve herd immunity either by vaccination or by spread of an epidemic. Generally, the individual, so in more general literature, individual heterogeneity lowers disease-induced herd immunity, but household structure goes the other way and actually increases it. We can't analyze HD very easily, but it's approximated well by Hg tilde in a lot of cases, and we can analyze Hg tilde. And kind of that's the key message from this talk, is that we can find these results about Hg tilde, which sort of carry over nicely to HD. And then very briefly, some future work combining these two together. So having an activity and household structure model, where we know one increases Hg tilde, one decreases it. What happens if we put them together? What happens if instead of having fully connected households, so households all mixing at one global rate, we have some households which connect with others more on sort of a network model? And the impact of a word I probably shouldn't remind us all of, lockdown on herd immunity. This is sort of an idea. It's not been fully fleshed out yet, but there will be work on that hopefully in the future. Okay, I think these are the references. This one at the top in particular is the one I want you to go and have a look at if you're interested. But I think that's all in terms of the talk. How are we doing for time?
We have a few minutes here for questions. Thank you, Liam. That was a really nice talk.
Thank you.
Do we have any questions from the audience? All right, so barring that, I'm going to start with what seems to me to be the obvious question. Um, what happens if you are to reduce the assumption that once people hit the recovered stage that they are removed from the population? You know, clearly with COVID, you have a significant transition back from R to S. How would that change your model? Have you looked at that?
We haven't looked at that in great detail of present, but I do see it's a good question. It's kind of, if you think in the vaccination standpoint, it's a little bit like saying what happens if the vaccination probability is not perfect. So what happens if the vaccination has some chance of giving you immunity? And I think the answer is that things do get more complicated, especially if you allow reinfection. So we haven't sort of considered this in detail, but it would be worth potentially looking at moving forward.
Okay, so there was a request, by the way, that you put the slide with the references back up so that people can see it.
Yep.
So a follow-on question, which I realize this is getting into practical epidemiology and not the mathematical modeling that you're discussing, but the question of estimating lambda L. How would we understand the rate of transmission within household? And do you have any thoughts or comments on that?
Yeah, so I haven't done a great deal of work on that, but I believe a previous PhD student who also worked under my supervisor Frank, one of his chapters of his thesis was to do with estimating the within-house local infection rate in these kind of models. So I'm not going to pretend I'm fully aware of the details of the paper, but certainly there is work done in that area to come up with good estimators for this within-house infection rate. I think in that paper, the within-house infection rate is actually a function of the household size as well. It scales with the household size, so you can be quite general with it. But yeah, there is literature that does that sort of thing.
Yeah, no, I've seen some literature that tries to get at it. It would seem that with the level of contact tracing and reporting that we've had, it would seem getting a really good data on that from an epidemiological viewpoint is challenging.
Yeah, for sure.
Okay, do we have any other questions? Okay, well, hearing none, I guess I'll just say, so here is a question. Can you include age structure in your analysis?
Yes, so this one of the extensions talking about activity level with household structure, it's possible to do a similar thing, but with age and household structure, provided we have some kind of idea about what rate at which members of different ages mix, then yes, yeah, it would be possible to combine. If you think about, if you have individuals typed by age and activity level, for example, then really you still only have one type. It's just type 1 could be the first age bracket and the first activity level bracket, and you could kind of stratify them all back into one type. But short answer, yes, you could.
Right, very good. Okay, well, it's the top of the hour now, so I want to respect everybody's time, and I want to thank Liam for a really nice talk. Really appreciate that, particularly at this late time of day for you over in the UK. So thanks, everybody, and we'll join you back at the end of February for the next webinar in our series. So please be on the lookout for the announcements. Thanks again, and take care.
Thank you very much.
Bye.